Okay, everybody, let's take a look at the notes for 6.1. We are beginning to talk about the normal distribution, and the main idea of 6.1 is this rule known as the empirical rule. Okay, so first of all, let's talk a little bit about the normal distribution. We've now looked at a couple types of distributions. We talked about the binomial distribution, the uniform distribution, and now the normal. Now, a lot of things in the real world follow the normal distribution. So it could be the heights, average heights of males, average heights of females. Notice, well, it could be, gosh, there's just countless examples. IQ scores follow normal distribution. And they all have this unique bell shape to them. Sometimes the bell is very wide and low, and other times the bell shape could be very tall or kind of narrow like that. But they all have this general bell shape. The mean is right smack dab in the middle of all these guys. Okay, the mean would be right in the middle, and it turns out that the standard deviation helps determine how spread out or narrow these things are. When you have a large standard deviation, you have a lot of spread and you get something like this. When your standard deviation is small, you have a little bit of spread and your bell-shaped curve looks a little more like that. But these are all normally distributed. Now, for the binomial distribution and the uniform distribution, we had some characteristics to check to verify that, oh yes, this random variable does follow a binomial distribution. Remember, we had bin. Or for the uniform distribution, it had to be a continuous random variable with all probabilities were equally likely. With the normal distribution, there are some criteria to check, but it's not easy to do, and it's a little beyond our scope right now. So really, we either need to be told that it's normally distributed or told that it's bell-shaped curve, and therefore we will know to apply our normal distribution rules, one of which being the empirical rule. Okay, now one thing is all of these are normally distributed. All these things I've drawn onto the side, or I tried to draw something bell-shaped. But they all have different means. Like this mean is a little to the left, it's smaller than this guy. Again, they have different standard deviations. There is a thing known as the standard normal distribution. And what you do is if you were to take one of these curves and you were to take all these data values here and you were to find their corresponding z-score. So remember, we talked about how to find a z-score. There's a reminder right there. It's your data value minus the mean over the standard deviation. If you were to do that for every single data value here, find the z-score, what you end up getting is what we call the standard normal distribution. And it is going to be another bell-shaped curve, all right? And it's going to be another normal distribution, but this time it's going to have a mean of 0 and a standard deviation of 1. We like working with standard normal distribution because it allows us to take these things that are normally distributed, but they might have different means, different standard deviations, and through one process we could basically shrink them all down to the same picture, okay? And it makes it easy to make comparisons between the two sets of data. So more on that later. The big thing we need to get out of here is the empirical rule. Okay. What the empirical rule tells us is that when we have a normally distributed curve, whether it's a wide one, narrow one, low mean, higher mean, doesn't matter. Every normally distributed random variable will follow the empirical rule. Now, it's not 100% dead on accurate, but it's a pretty good representation or a pretty good approximation of what the data is doing. Now, what this tells us, and here they've shown us a generic normally distributed curve, the mean right at the middle, right? Okay. So what we see is that if you go one standard deviation to the right and one standard deviation to the left from the mean, it turns out that all of that space right there all of that area contains 68% of your data, okay, or pretty darn close to it. All right, so whenever you go one standard deviation on either side of the mean, you create a little window that scoops up 68% of all the data in your that your random variable is giving you. If you were to go 2 standard deviations to the right and 2 standard deviations to the left, all of this area that covers 2 standard deviations left and right of the mean, that covers 95% of your data. 95% of your data lives within 2 standard deviations of the mean. And we talked about that earlier. That's why in probability we sort of use the 5% cutoff as being considered too unlikely, too low probability, and therefore possibly an outlier. Anybody that lives out here is not within that 95% realm, and we would consider that a little abnormal, beyond 2 standard deviations from the mean. If you do go 3 standard deviations from the mean, the empirical rule tells us that all that area from 3 standard deviations, both sides of the mean, 3 standard deviations right, 3 standard deviations left, you will scoop up 99.7% of your data. So almost 100% of your data lives within 3 standard deviations of your mean. Okay, there's still a little bit of data outside of that, but definitely the bulk is within that window. Really, the bulk is within 2 standard deviations of the mean. That contains 95% of our data. Okay, we are going to see more and more uses of this. The point of 6.1 is to get us familiar with working with empirical rule and basically finding percentage of data in the area here under these curves. Okay, and once we get our hands with feeling okay with that, we're going to actually put some examples together with them. So we're talking about z-scores and the standard normal distribution. Again, all of these are normal distributions because they're bell shape, or I tried to draw them bell shape. It becomes a standard normal distribution when you look at the z-scores of all these data values, and that's going to give a mean of 0 and a standard deviation of 1, and it standardizes that normal distribution. Makes it easy to analyze. Okay, so here they're telling us that, again, if the data values are normally distributed themselves, like all of these guys I drew on the right, then their z-scores will follow the standard normal distribution that has a mean of 0 and standard deviation of 1. For this first example, we are not going to standardize it, though we can. I think I'm just going to wait and, yeah, we don't need to standardize it to get through this example. But we will be doing that pretty exclusively beyond this. So take a look here. It says the golf scores for a school team were normally distributed with a mean of 68 and a standard deviation of 2. Find the probability that a golfer scored between 66 and 70. Okay. I don't know about you, but I want to sketch up a little picture here. So first of all, they tell me that my golf scores are normally distributed. So the golf scores follow some sort of a bell-shaped curve. I'm going to give myself a little more room to work with here. Now they say that the mean of the golf scores is 68. So that means the middle value is 68. Okay. And there's a standard deviation of 2. So in other words, I'm going to just kind of count by standard deviations. If I go 2 to the right, that would be 1 standard deviation would put me at 70, right? Because I would bump 2 points to the right. Another standard deviation would put me at 72, and another standard deviation would put me at 74. Because again, each standard deviation is 2 points. Let's go left. If I go left 1 standard deviation, I'm at 66 because I dropped 2 points. Another standard deviation, I'm at 64, and another one, I'm at 62. So they ask you, find the probability that a golfer scored between 66 and 70. Well, looking on my chart here, 66 and 70, that is the percentage of data that fits between 66 and 70, right? Now remember, empirical rule tells us how much data lives under here, but don't we know that also we just learned that area under the curve is probability? Area under the curve is probability. So what empirical rule just told us is that if you go one standard deviation to the right and left of your mean, you scoop up 68% of your data. This little window that's now getting very cluttered, if I just go one standard deviation left and right, then I am scooping up 68% of my data. Or in other words, the proportion of the data that's under this curve is 0.68. Okay. I wish they would have chosen a different number, all right, because now it's kind of confusing with the mean. That's just random luck, all right. But I know that this area right here, because I went one standard deviation left and right of the mean, I know that that area is 68% of my data. And since it's area under the curve, that's also my probability. The probability that they scored between a 66 and a 70, probability score between 66 and 70, yikes, that is equal to 68%. Okay. Now, let's try this next one. It says, between what two scores does the team score 95% of the time? So looking at our distribution here, between what two scores would we expect to find 95% of all of our data, or 95% of all of our golf scores? Again, going back up to empirical rule, if you were to go 2 standard deviations left and right, you would scoop up 95% of the data. So if I were to just look 2 standard deviations left and right and highlight all that region there, that would be 95% of all my data, or the probability of landing in that green zone would be 95%. So if I'm looking for the 95% marker, I know that I need to go 2 standard deviations left and right of my mean. Again, a standard deviation is a score of 2 points. So there's one standard deviation, there's another standard deviation. Let's go left 2 standard deviations. 1 standard deviation, 2 standard deviations. So this region here, the highlighted green part, that contains 95% of my data. Golf. Okay, so between what two scores does the team score 95% of the time? 95% of the time, the team scores between 64 and 72. Thanks to the fact that we know golf scores in this case are normally distributed, so they follow the bell-shaped curve, and therefore the empirical rule applies. Meaning you go 1 standard deviation left and right, you hold 68% of the data. You go 2 standard deviations left and right, you hold 95% of the data. And when I would go 3 standard deviations left and right, that would hold 99.7% of the data. Now I just noticed part C here, it says draw the normal model. That's what I did there. I just did it off to the side. On the next page they've actually got a blank one for us, so let's just put that there, because then they're going to ask us some more questions, and personally I think these questions are easier to do by making a little sketch. So they've given us a generic normal curve. Again, the mean is 68, okay, right down the middle. Every standard deviation, or a standard deviation, is 2 points. So if I go 1 standard deviation right, that's 2 more points above 68, so I'm at 70, another standard deviation, and another one. If I go left standard deviation, I drop 2 points, another standard deviation left, and another one left. And again, if it's helpful, I'm just going to add these in. I'm going to say, okay, between here and here, that's 1 standard deviation. That's 68% of my data that fits there. Again, it has no relation to the fact that the mean is 68. That's random that those are the same number. This should be a different number to not make things confusing. And if I were to look between these two numbers, that's 2 standard deviations left and right, so that should contain 95% of my data. And if I were to look between these two numbers, 62 and 74, that's 3 standard deviations to the right and left, and so that should contain 99.7% of all my data, according to the empirical rule. Not exactly, but a really good approximate, and I could use those to answer some of these basic probability questions here. Because again, when you're talking area under the curve, you are talking probability. 1 second. Okay, I'm back. Not that you can tell the difference. It just flashed in and flashed out. Okay, we could answer all of these using the empirical rule, all right? And people do them different ways. For me, I definitely prefer a little sketch. It helps me out. Anyways, it says what percentage of the scores would be between 68 and 70? So I'm just going to kind of draw a quick little sketch. Between 68 and 70. That's 1 standard deviation to the right, correct? I'm just looking for that little gap there. Well, I know if I go 1 standard deviation right and 1 standard deviation left, that altogether that contains 68% of my data. So aren't I really just looking for half of that, right? I'm not looking for a standard deviation left and right. I just want 1 standard deviation to the right, because I want only between 68 and 70. So I would just take this figure, I know 68% is a standard deviation left and right, and cut it in half. And so what I would get is 34% of the scores are between 68 and 70. Okay, find the probability that a golfer scores between 64 and 68. So if I think of my curve, again, 68 is the middle, that's the mean in this case. 64, that's 2 standard deviations to the left. Right? Because again, a standard deviation in this case is 2 points. So this is what they're asking me for. Find the percentage of people that live there, or the probability of landing there. I know if I went 2 standard deviations left and 2 standard deviations right, that whole thing there, 2 standard deviations left and right, covers 95% of my data. But kind of like the last example, don't I only want half of that? I'm not looking for 2 standard deviations left and 2 right. I'm only looking for 2 standard deviations to the left. So similar to above, it's going to be 95% cut in half. So that would be 47.5% of golfers scored between 64 and 68. Okay, so that's how the rest of this section is going to go. They're going to ask us a variety of these types of questions that we are going to have to use the empirical rule to dig our way out of. Now, what this is going to get into is, well, what happens if I go like 1.5 standard deviations left or right? Then the empirical rule kind of breaks down, because it only tells us how to handle 1 standard deviation left or right, or 2 standard deviations left or right, or 3. Any other number than that, like 1.5 standard deviations, we either need to rely on some technology to help, or a z-table, which we'll get into shortly. Anyways, let's just keep chugging along with this. Find the percentage of scores that fall between 64 and 66. Okay, so there's 68, there's the middle. 66 is a standard deviation left, and 64 is a standard deviation left of that. Now, what they're asking me to find is just this part right here. Okay, Again, I could do this two ways. One thing I just learned is I just learned from this last problem that from 64 to 68, there, that distance contains, what was that, 47.5% of my data. Now, if I could figure out what this contains, then I could just take the 47.5% and subtract that part away. Well, this is only one standard deviation to the left. It would be the same as if we went one standard deviation to the right. It's half of 68%. Right? Because again, if I go one standard deviation left and right, in total it's 68%. Any half there is 34%. So maybe I'll start adding things. There's my mean. I know that if I go one standard deviation to the right and one standard deviation to the left, we found that this is 34% in here, and this is 34% in here, for a grand total of 68%. So anyways, I know that this little chunk here is 34%. So to get this blue shaded part, I'll take the big piece, the 47.5%, and I'll subtract out the 34% that I do not want. Right? I'm taking all of this and I'm subtracting out this little part that I do not want. And, well, that'll come out to 13.5%. Score between 64 and 66. Right, so they get a little trickier as they ask for different pieces of the puzzle, but you can figure them all out by using this empirical rule. And if I want to add it to my little picture here, what I just figured out is that if I go down to 64 here, that little sliver we just found is 13.5%. Well, it's going to be this by symmetry. It's the same as this sliver over here, 13.5%. Sorry, that's getting real small. If I were to add up all of these, what should they add up to? They should add up to 95% because I went two standard deviations left and right. All of those should add up to 95%. Okay, let's keep chugging along. What's the probability that a golfer scores higher than 68? Well, 68's the middle. So the probability that someone scores higher than that would mean that they live on this side of the curve. Remember, probability is area under the curve. Okay, so wouldn't that just be 50%? It's the upper half of the curve. So there's a 50%, or the probability they score higher than 68 is 50%. Okay, let's give this one a shot. Find the probability that a golfer scores lower than 62. So 62 is low on the score, right? So here's 68, the middle ground. I go a standard deviation left, I'm at 66. Another one, I'm at 64. And 62 is 3 standard deviations to the left. And I'm trying to get lower than that thing. So I'm trying to look for that area right there. Okay. Well, think back to imperial rule. If I go 3 standard deviations left and right, right? So stop it, cat. If I go 3 standard deviations left and right, so 3 left, 3 right, this whole area here, according to empirical rule, is 99.7% because I went 3 standard deviations left and right. That means that these 2 little green slivers here, what is left, this sliver and this sliver, together make up the rest. So in total, these pieces are 0.3%, right? That would be the leftover to get this thing up to 100%, all the data, right? Well, I'm not interested in landing in both of these locations. Aren't I just looking at being here only, right? I want to be strictly less than 62. So I'm not interested in this sliver. Doesn't that mean I should take this amount here that represents the total green area and cut it in half, right? So the probability of scoring lower than 62 would be half of 0.3%, which in this case I believe that's 0.15%. Very low probability that you're going to score under 62. Right? Okay. Let's take a look at the second example, which is the same thing, except here they're not using a real-life example like golf scores, and they're actually talking about a standard normal distribution. Now, this notation here, every distribution has its own notation that different books use differently, but this is basically saying that the data is normally distributed. This would be the mean of that distribution, and then this is actually the variance, which we write as sigma squared. Do not get hung up on this at all. I just want to explain what the heck that means. Instead of spelling out in words, the data follows a standard normal distribution. You know, math people don't like writing all that, right? So we just try and shortcut it with some symbols. So that's all this is. There's also one for binomial and uniform that I'll try to remember to mention later. Anyways, they say that we are on a standard normal distribution. So what that means is I'm looking at a normal distribution. Because it's a standard normal distribution, the mean is 0. And every standard deviation would be 1. I mean, here they're saying the variance is 1, but if you square root that to get standard deviation, the square root of 1 is 1. So this would be 1 and 2 and 3. These are the number of standard deviations I go to the right, and -1 and -2 and -3. Those are the number of standard deviations I go to the left. Standard or not, this is normal, right? So it follows the empirical rule, again, meaning that from one standard deviation left and right, there's 68% of your data. So when it comes time to do this probability, what's the probability of getting a z-score? Again, all of these are z-scores. That's how we create the standard normal curve. We say, don't worry about these golf scores, let's convert them into z-scores, okay? Using that formula. It's your data value minus the mean over your standard deviation. That'll take every data value and convert it into a z-score. And again, we're going to see later why we like the standard normal curve, because it actually doesn't matter so much when you're using like technology like StatCrunch. StatCrunch can handle these numbers no problem. You tell it what the mean is and what the standard deviation is, and StatCrunch will do your probability. However, a tool that lets us do any one of these problems is a z-table, and a z-table is based on a standard normal distribution. So if you want to use a z-table, you've got to be talking about z-scores. More of this is coming later. Again, I'm throwing a lot out at you. The point of this lesson is to make sure you've got your head wrapped around empirical rule. That's it. Okay, so just focus on getting empirical rule, and the rest is going to fall into place. Anyways, the probability of getting a z-score in between -1 and 1, they're talking about getting a z-score there. Well, remember, the area under that curve is 68%. Area under the curve is probability. So there's a 68% chance you'll get a z-score between -1 and 1. Here I'm looking at what's the probability that I get a z-score between 1 and 2. I don't know that I'll draw this out every time, but let's see. There's the mean, 1 standard deviation, 2 standard deviations, and 3. They're asking me to find what's the probability of landing here. Okay. I think we could sort of utilize what we've already done. Don't we know that from -2 to 2 standard deviations is 95% of your data? So if we cut that in half, don't we know that from 0 to 2 standard deviations on the right, like if I only go 2 standard deviations to the right, it's half of all that distance. We said that was 47.5%. And because we know that from 1 standard deviation left and right, that's 68% of my data, didn't we say that from just 1 standard deviation to the right that was half of that number? That's 34%. So this is exactly like what we did in one of these examples here, right here. If I want to know the area under this portion of the curve, or what's the probability of landing in this blue region from a z-score between 1 and 2, I know that this little gap here can be found by taking 47.5%. That's this whole distance, and then subtract out the part you don't want, minus the 34%. And so we're left with, we said that was 13.5%. That's the probability of getting a z-score between 1 and 2. Okay. This takes a bit of practice. And I know I'm going through it fast, but again, my thought is you're going to stop and pause and rewatch this thing more than once. But once you get your head wrapped around the empirical rule, right, this doesn't become too bad to do. So I believe there's just one more page with a few more problems on it. Let's give those a shot. Same deal. We're talking about a standard normal curve. And I know we are just by the fact that they're mentioning z-scores. So again, I'd like to have a picture when I'm doing this. Standard normal has a mean of 0 and a standard deviation of 1. So I've just counted out a total of 3 standard deviations right, 3 left. For this problem, they want to know what's the probability of getting a z-score bigger than 2. Again, you could do this a variety of ways, but didn't we just learn that, or not long ago, that this area from 0 to 2 standard deviations to the right, just to the right, not 2 left and 2 right, but just to the right, didn't we say that that was 47.5%? Because if I were to go 2 to the left and 2 to the right together, that would make up 95%, right? That is 95%. So if I'm only doing half of that, it's half of 95%. Now another thing I know is, don't I know that from here onward, from the middle ground onward, isn't that half your data? Okay. So what I could figure out is that if I want to know just this yellow part, I know that from the mean all the way to the right is 50% of the data, and what I'm not interested in is I do not want that chunk of the data, right? Because that's not in the yellow region. I want only to the right of that. So couldn't I take 50% of the data and subtract out that chunk I don't want? So that looks like it should come out to 2.5%. How about getting a z-score less than -1? And you could do these, there's more than one way to do these, okay? But I do think the graph helps. So I'm just writing out my standard normal curve, and I'm showing 3 standard deviations going both ways, so we could use empirical rule. I'm looking for the probability of a z-score being left of -1. Remember, probability is area under the curve, so what they're asking me for is what is that area there? I think I could sort of probably do this in a similar fashion. Don't I know that from here, from the mean all the way left, is half of my data? Okay. And if I could figure out what this gap is, that's the part I want to remove. So if I could figure out what that is, I can just subtract it from 50%. Get rid of all that, and I'll be left with just the highlighted yellow part. Just that part is all I want. Okay. Well, since this is one standard deviation to the left, didn't we learn that if I go one left and one right, it's a total of 68%? And so we said that just one left by itself is 34%. It's half of that. Okay, so if I want this piece, I could just go 50% the whole thing and subtract out the 34% I don't want. Right, so the probability of getting a z-score less than -1 would be 16%. Let's try these last two here. Mean of 0, just doing the same picture. My mean and my standard deviations from the mean. Here I'm looking for the probability of getting a z-score that lands in between -1 and 3. So that would be all this area here. Okay. So what I need to do is I need to get rid of this stuff. Oops, I'm trying to erase it without erasing everything. Oops, that's not helping. We're sorry that you crashed. Come on. Hold on, guys. Okay, I'm going to pause this video. Oh. Okay, I'm going to pause this and get back to you. I'm back. I guess this thing is having enough with stats. We're almost done. I'm looking for the probability of getting a z-score between 1 and 3. And again, when I'm working on a standard normal curve, all these data values here are z-scores. How can we do this? Well, I'm going to kind of use what I just figured out from the last problem. The last problem said that the probability of being here, left of -1, we just found out that all of that probability was 16%. Right? I'm just looking at what we did there. I also know from a previous problem that this little shaded region, just one arm of that shaded region, oh no, I don't know what that is yet. I don't think we figured that out, did we? Well, let's go ahead and figure that out in case we didn't. No, we did that one. Isn't that to be to the right of one arm to the right of 3 standard deviations? Didn't we say that that was 0.15%? That was an example or two back, I believe. Let me see. Yeah, right here, the golf score. Okay, so I'm just going to take what we've already learned. So what I want to do is I want to get only the yellow region. I want to exclude these regions. Well, what is the total area under this curve? Isn't the total area there 100%? Right? So this yellow shaded part I want, isn't that 100% minus the 16% I'm trying to get rid of here, minus the 0.15% I'm trying to get rid of here? Right? So what is that? 100 minus 16.15 is 83.85. So if I'm doing the math right, this should come out to 83.85% would be the probability of landing in that yellow shaded region there. And the last one, I want the probability of getting a z-score between -2 and 1. So again, there's my mean, a standard deviation left, another left, and another left, a standard deviation right, another right, and another standard deviation to the right. I'm trying to get a z-score between -2 and 1. So that's the area that I'm looking for. Okay. I'm trying to think back to any of these previous problems and see if we could make use of any of the stuff we've already done. I'm not seeing any directly on this page, so let's just solve this one. Let's just figure this out. I could take the same approach. I could figure out, okay, the whole thing is 100%, so if I could ixnay this part and ixnay this part, I've got it. That's one option. Another option here is actually from previous work. I mean, I know this whole thing is oh no. I'm going to pause again. Hold on. Okay, just came back from another crash and I realized I'm not certain I hit record when I did this problem. So if I didn't, I apologize. I'll just really quickly, what I did is from previous problems we could figure out that this was 16%, right? That was from part D. And from another problem we knew that this little sliver was 0.15%. So I said let's take the whole 100% of the area and subtract out the pieces we don't want. All right, and that's how we got this number. Okay, let's do this last one before this thing crashes again. I've got a mean of 0, standard deviation 1, 2, there's 3 standard deviations to the right, 3 standard deviations to the left, and I want to be here. Apologize for all the crashing. I'm not quite sure what that's going to show in the recording. Okay, quickly, one option is, again, and if I've already said this, forgive me, but one option is to do what we did here, which is to realize like, okay, well this whole thing is 100%. If you can figure out what that is and get rid of them, you'll be left with just the yellow shaded area. Another option is, I know that from the mean, if I go 1 standard deviation to the right and 1 left, that's 68% of my data. Right there is 68%. So I just need to figure out what's in this little arm here. Well, I know that if I go 2 standard deviations left and right, it's 95%. So actually, let me break this up. If the whole thing there is 68%, don't we know that this is 34%, we said, and this is 34%. And since this whole thing here, 2 standard deviations left and right is 95%, didn't we say that half of 1, this whole thing here would be 47.5%, because I'm taking half of this number. Things are disappearing quick, so I'm just going to finish this problem and turn off this computer. But I hope that makes sense. Again, a standard deviation left and right is a total of 68%, so I know that this arm has got to be 34%, as well as this little arm. But I also know that when I go 2 standard deviations left and right, I get 95%, so 2 to the left would be half of that. This all here is 47.5%. So one option for me would be to just add those two numbers together to get the total area. I went 47.5% left and 34% right. So the probability of getting a z-score in between those guys would be the sum of those two probabilities, which if I do it right is 81.5%. Okay. That was a lot thrown at you. I hope you're still hanging with it, and I hope it went fairly okay with all the crashing at the end. We took a big jump here, kind of talking about the normal distribution and then just going right into standard normal distribution and z-scores. Again, what you really need to get out of this section, 6.1, is know how to work with the empirical rule. All right? Know that whether you're on a standard normal distribution or any one of these normal distributions, that when you go a standard deviation right and left, that covers 68% of your data, whether it's on this guy, or the fat one, or the skinny one. One standard deviation left and right covers 68% of your data, 68%. 2 standard deviations covers 95%, and 3 standard deviation covers 99.7% of your data if you go 3 standard deviations left and right. Okay, and that's the exact same thing as probability, because again, probability is area under the curve now, we've learned when we're talking about a continuous random variable. And then the whole idea with normalizing these is, again, standardizing, I'm sorry. You could have a variety of normal distributions, wide, narrow, means all over the place. When you take all of your data values and convert them to their equivalent z-scores, you then create the standard normal distribution, which is what this is. These were standardized because we're dealing with z-scores here. The golf thing was not standardized because we were not dealing with z-scores, we were dealing with the raw golf scores. If I were to convert these all into their z-scores, you would get another bell-shaped curve, but it would have ones and a 0 for the mean and 1, 2, 3 for your standard deviations. Okay. All right, we're going to do more with this later, so hang in there. Again, the big focus for now is make sure that you can do these problems utilizing empirical rule. Know how to find these areas like I was doing for all these. That's the big idea, be able to find those areas. Okay, I'm going to sign off and post this video.